Hey everybody. Today we're analyzing college data using R. The college data set can be found on Kaggle with a simple Google search. I'm going to be using the version that's included in the ISLR2 package. That's a package of data sets supporting the excellent textbook Introduction to Statistical Learning with Applications in R. I've already loaded up that package along with Tidyverse. To start out our data analysis, let's just find out a little bit about our data set. We shouldn't be complete strangers in this. Since it's a data set I've loaded in directly from R, there should be a help file. Let's pull that up with college, and there it is. You can see it there. We have data from a 1995 issue of US News and World Reports. It's not exactly fresh data. If you're trying to decide where to go to college in the United States, this probably isn't your best source of information, but it's a great data set for data analysis practice. We can learn a little bit more about the data set here. There's a data dictionary. In particular, we can see all the variables and get a little information about what these variables are representing. Let's learn a little bit about the data itself with glimpse. There's lots of ways to get into a data set using R. The summary command is another good one. I want to glimpse college. You can see that we have 777 observations, rows, 18 columns, variables, and these are all numerical except for private, which is a factor variable. In this vid, I'm going to be interested in whether graduation rates tend to be lower at schools that have larger full-time enrollments. So I'm going to be using F undergrad as a stand-in for the size of the college. And you can see there's other variables here that might work as well. I've picked this one almost at random. Later on, I'm also going to be interested in the private variable. Is the school public or private? And the top 25% variable. And that is going to be a little bit of a stand-in here for how selective the school is. Again, there's other ways that you could measure that. I've picked that one for simplicity and also just a little bit arbitrarily. Okay, so now we're ready to get started on the data analysis with some exploratory visualizations or graphics. We want to do a little bit of exploratory graphics for at least two reasons. First of all, just to try and get to know our data set a little bit, try and get some insights into the data. Just by looking at the data, a lot of times we'll see patterns that'll lead us along new paths in our investigation. Secondly, when we start to get into inference techniques, those are all going to be dependent on the distributions we're using. So we want to make sure, at least on the face of things, that those inference techniques are going to be justified. So the first thing I want to do is to use the college data set, of course, just to get a histogram for this response variable, grad.rate. There we go. We'll leave all the defaults to start. Just maybe lower this a little bit. Okay, so some good news and some bad news here as I look at this histogram. Good news is it's got a generally bell shape. That always makes me happy. That feeds into certain statistical inference techniques, potentially. Secondly, bad news, there's this weird outlier over here to the right. You can see there's some college that's off to the side of everything else with a graduation rate of, I don't know, maybe 120%. And that raises a flag for me because graduation rates are percentages. It doesn't seem like they should go over 100%. So note the weird outlier. Let's investigate that just a little bit more. Let's do a filter, and we'll save the output of that filter as a data frame called suspicious. So the filter is going to take the college data set, and it's going to keep all the columns, but eliminate some of the rows. And in particular, the only rows I want to keep are going to be the ones with grad.rate greater than, let's do greater than or equal to 100. And then we can view that. Okay, so 11 of these 777 colleges reported graduation rates of 100% or more. You can see that all except for one of them reported the graduation rate of 100, whereas this one, Cazenovia College, reported a graduation rate of 118%. Now, a lot of the colleges on here are pretty reputable. Harvard's even on here. So I suspect that this is not fraud or even misreporting, but rather there's something going on here that we're just not seeing in the data set. Maybe students that graduate with more than one degree are being counted twice in the graduation rate, something like that. In order to really figure out what's going on here, we need to step outside the data set and do a little research. If this were a full data analysis, not just a shorter YouTube video, I would be doing that. As it is, I'm just going to take this data on at face value and move on with my analysis. Okay, so the next thing I want to do is a scatter plot with the two primary variables I'm interested in. So this time I'm going to put the primary explanatory variable, which is going to be full-time undergrad, on the x-axis, and graduation rate on the y-axis. And since it's a scatter plot, I want a geome point. Maybe I'll zoom in on that. Okay, so that's a little bit off to the corner. I don't know why. I'll fix that in a minute. So you can see the data is all clustered over to the left. Things are crunched in. There's more smaller schools than larger schools. That makes sense when you think about it. Now, when I see data like this, quantitative variable all crunched into one side, I wonder if a logarithmic transform might be helpful. So I'm going to do a log base 10 transform. It doesn't really matter what base I use, but log 10 is fairly easy to interpret. And that's going to give me something a bit more cloudy. Let's zoom in on that. Nice cloudy shape, good candidate for a linear regression. So the log base 10 is essentially taking the raw data, the raw size of the school in terms of full-time undergraduate enrollment, and instead giving me information just about the scale. Is it on the order of 1, 10, 100, 1,000, 10,000? So these are exponents for base 10. Once we do that, we get this cloud. And this transformation makes sense because it's not so much the exact size of the school that matters, but the scale of the school. Is it a giant school, a mid-sized school, or a very small one? Okay, as long as I'm doing this, since I'm going to be using the log base 10 of these undergraduate populations as my primary explanatory variable, let's go ahead and add that variable to the data frame. So I'll call the new data frame college small, and I'm going to start with college. And let's use the pipe to send that as the first argument into the next function that I'm going to write. So the first thing I want to do is add a new column called log full, and that's going to be log 10, base 10 of F undergrad, just like I had a little bit ago. Then after that, let's just only keep a few of these columns. Let's keep grad.rate. Let's keep log full. Let's keep private. And let's also keep top 25%. And since I'm going to be working with this one for the rest of the vid, let's put it up on the viewer. We'll have an open tab for that. Close the suspicious one. All right, so as I said, grad rate, log full, private rate, private, and top 25%. Notice we still have 777 rows. Neither mutate nor select is going to remove any rows from our data set. These are just doing things with our columns. All right, let's do some modeling. I said I had a good candidate for a linear regression, so let's do it. Let's start just by doing it visually, I think. So I'm just going to take this, this picture that I have and put on a smoother. So the default is a low S curve. I want a linear model. Big enough data set where I don't think the standard error ribbon is going to be too distracting, so I'll just leave that on. Okay, it looks pretty flat to me. That seems to indicate that undergraduate population, full-time undergraduate population, isn't a great predictor of graduation rates. Let's get the actual linear model, the regression equations, p-values, stuff like that. See if the numbers bear out that observation from the visualization. Let's call it model undergrad to distinguish it from a couple other models that I'll probably make later. And I want to do LM, linear model. Response variable is grad.rate. And I want to do that in terms of log full. And my data set, of course, is college small. All right. Let's see it. There's a method for a linear model object like this for the summary command. So we can use summary of model undergrad. Let's see what we get. Let me mess with these windows a little bit so you can read that a little bit better. There we go. Okay, so we've got our coefficients here. This is going to be the slope of that line that we saw, and this is going to be the y-intercept. The slope is very, very small, not even 0.1. Notice the p-values. In particular, the p-value for that slope coefficient is 0.95. Not a small p-value. Remember, p-values go from 0 to 1, with smaller p-values indicating higher statistical significance. So the rough and ready explanation for this is that, in fact, the full-time undergraduate enrollment is not a meaningful explainer of the graduation rates. Okay, so the short answer to our first question here, do colleges with full-time enrollments have lower graduation rates, seems to be no. One thing I want to do before I start looking at some of these other variables, as long as we're doing a linear regression, let's go ahead and get diagnostic plots for this. And I want to do diagnostic plots in the simplest case here before I move on to anything more complicated, just so that we can make sure we're all on the same page about what's going on here. So plot is in base R. The graphics we get out are not going to be pretty. These are just going to be for our own reference. Okay, so we're going to get a sequence of 4 plots in this interactive console session here. And they're each going to give us information about the different assumptions of linear regression. The first is just a regular old residual plot. And this is indicating to us whether or not there's a generally linear shape between these variables. Here you can see we've definitely got a cloud. The red line here is relatively flat. You can see a little bit of a inverted V shape, but nothing too extreme. So there does seem to be a linear shape here. We just end up having a 0 slope to that line. Next up is going to be a normal QQ plot. This is indicating whether our residuals are normally distributed. That's another assumption of linear regression. Here things look pretty good until we get to the far right. And that actually makes sense since there's essentially an upper bound on how big our graduation rates can be, 100%, with the exception of Cazenovia College. We have just some inherent skew in our data. Nothing too horrible. Next up is the scale location plot. This is giving us an indication about the homoscedasticity of our data. Is the variance in the response variable relatively constant for different values of the explanatory variable? Here again, we're looking for a horizontal-ish red line with no major patterns noticeable in our plot. And we've got that here. Finally is residuals versus leverage. This can give us indications of whether we have problematic outliers that might be messing with our model in an undue way. Here we don't have any problematic outliers. If we did, there would be a dotted line somewhere on here representing a threshold for Cook's distance with a point beyond that threshold. Okay, so diagnostics look good. Maybe I'll return to diagnostics on a later plot. If not, you should do so on your own. Okay, so what about private? Does private matter? Is this going to change things? So I think the first thing I want to do, again, is to get a visualization. Let's actually put in regression lines. So I'm breaking this plot down now according to public and private institutions. So that's that categorical variable, factor variable, and I'm going to plot it using color. The variable is private. There we go. And this time I do want to take out the standard error ribbon. Seems to be getting a little cluttered with that in there. Okay, so now we can see some differences between the public and private schools, and we can see that it does have an impact on our regression lines. So private schools here are in the bluish, and the public schools are in the reddish orange. You know what? The base the default color scheme for ggplot is not colorblind friendly. I want to fix that, accessibility or bust. So scale color brewer and palette dark 2, which is a colorblind friendly palette. All right, now I feel a little bit better showing this plot publicly. All right, so now the private schools are in this reddish, this sort of burnt orange, and the public schools are in the greenish color. And we can see that the private schools tend to have graduation rates that are higher and their sizes tend to be smaller. So the cloud is just a little bit up and to the left versus the public schools. Notice that each of these regression lines now has a positive slope. So actually, as full-time undergraduate enrollment increases, as the scale of that increases in particular, graduation rates tend to go up. So maybe that's counterintuitive, maybe not. I began this video by asking, as undergraduate population goes up, will graduation rates go down? Visually speaking, at least, it looks like the opposite is true. So let's model this. I'm going to do the same steps essentially as I did up here in line 39, except now I want to add a variable to my model. So how about model private? Again, linear model. I want to model grad, not guard, rate. And I want to model it in terms of two things. First of all, is the school public or private? And then the second thing is going to be log full. Data is still college 2. And let's get the summary of that. And college underscore 2. Model private. College small. There we go. All right. And then we can see this model. Okay. There's the summary printed out. Okay, so let's remember what all of this means, especially in light of this plot. We've got two regression lines. So what R is doing is it's giving us the intercept and slope for the private schools. I'm sorry, for the public schools. And then it's giving us the intercept and slope for the public schools, so private no. And then it's giving us the difference in the y-intercept for the public schools. This is what we call a parallel slopes model. It's the default linear model here in R. I have a whole vid on parallel slopes models. I'll throw a link up top. The idea is that it should be modeling two regression lines that are parallel to one another. Notice the p-values here. The intercept that we're not so worried about is high, but the other two are very, very small, indicating that it appears that both public-private and the logarithm of full-time enrollment are both important indicators, are useful indicators of graduation rates. Also, while we're at it, notice the multiple R squared and the adjusted R squared. So multiple R squared is telling us, roughly speaking, the percentage in the variability in the response variable, here graduation rates, that can be attributed to or explained by the explanatory variables, so public, private, and the logarithm of full-time enrollment. So about 20% of the variability here. So that's something. Adjusted R squared imposes a little bit of a penalty for adding additional variables to the model, for making your model more complex and potentially overfitting your data. I'll generally refer to the adjusted R squared when I'm talking about this, when I'm talking about overall model fit. Okay, now, if you look at this plot, where'd my plot go? There it is. You're seeing probably that those slopes are not actually the same. The ggplot smoother by default goes with an interaction model. So let's take a minute and actually get those equations just to be consistent with the plot and see if that gives us a better model. So I'll write full undergraduate, but of course I'm looking at the log of that. All right, so I'm just going to copy and paste my model private. I'll call it model private int for interaction. And since I want private and the logarithm of the full-time enrollment to interact, I want to replace that plus with a star. And that's going to just put in a multiplicative term into our model. I have an entire video on multiple regression with interaction. I'll throw a link to that up top. So then let's get the summary of that. Okay, and I'll just run that again so that maybe it'll print out all in one nice, neat-ish table. Okay, so let's see here. Now we are getting two different equations of two different regression lines. We are getting the intercept and slope for public schools, for private, no. And then the difference in intercept and the difference in slope for private, yes. So for the private schools. So we could actually get the equations of the regression lines using those. Now let's look at the p-values. Private is no longer statistically significant here. The p-value has gone all the way up to 0.32. Log full and the interaction term are both statistically significant, although they're not exactly minuscule here. Let's remember what these p-values are really referring to. In each case, the p-value is testing the hypothesis that the null hypothesis that coefficient of that term is 0, and that the results are just due to random chance, under the assumption that all of the other terms are already in the model. In other words, assuming intercept, private, and log full are already in the model, what's the probability of getting results like this just by random chance if the coefficient of private times log full is actually 0? So some of our p-values have gone down a little bit counterintuitively. And one reason for that is that we are including private and log full in our model in two different ways. And so the impact of each of those variables is a little bit distributed. Okay, notice our r squared, in particular the adjusted r squared, 0.2069. Previously, we had 0.1995 right here before we included the interaction term. So our adjusted r squared has gotten a little better, but not very much. It is very much a comparable model in terms of the amount of variability explained by the model. In exchange, we've made our model substantially more complicated. We've added an interaction term, a multiplicative term. It's less easy to interpret and more susceptible to overfitting. So while you could keep that in, I would probably tend to drop it just as a practical decision. Let's see here. One other thing I think I will do before I move on here is to do an ANOVA on this, on model private int. I'll just keep that all together. All right, so the ANOVA is going to start with a null model, in other words, one where we just take the intercept and add in the variables one at a time. So first it's starting with an intercept, just the overall mean of the response variable, then adding in private, and then already having private in, adding in log full into the model, and then adding in the interaction term into the model as well. And then telling us sequentially whether each of those terms is statistically significant, given that the previous ones are already in there. Most of our values are different now. If we just put in private, yes, that's statistically significant as an explainer. If we just put in the logarithm of full-time enrollment, yes, that's statistically significant. Once those are already in, now we put in the interaction term. Also statistically significant, but not exactly infinitesimal. Again, this last one is assuming these other two variables are already in. Notice that's exactly the same as what we got out of the summary command at the very end. The p-value, assuming the other variables are already in the model. Okay, that's doing what we call a nested f-test, by the way. I'll make a video on that someday. We'll see. If eventually that happens, I'll put a link to that up top, but that's not on my immediate to-do list. Okay, so in each of these cases, we are seeing that when private is taken into account, schools with larger full-time enrollments tend to have higher graduation rates. Let's see here. So what about top 25%? That's the last thing I want to do. So now I've got three variables, three explanatory variables that I'm considering. So just looking at those three, there's 2 to the third or 8 possible models, because each of the three explainers can be included or excluded. A lot of choices. If we really want to get the very best model in terms of explanatory power, we need to think about some techniques. We either need to go by brute force, so we need to think about techniques like stepwise selection that I'm not going to get into here. All I really want to do right now is to take the additive model that I already have, that was model private, and include top 25% in it and see what happens. So how about model top is going to be modeling grad rate. Again, in terms of private, maybe I'll just start a new line so I don't go totally off to the edge. Log full. And top 25%. And my data should be college small. And let's get a summary on that. I could do another ANOVA. Maybe I will in a minute. We'll see. Summary ANOVA. Haha. Model top. Sometimes have trouble typing and talking at the same time. Okay, great. So now each of my variables is statistically significant, in fact has an infinitesimal p-value when the other variables are already in the model. So that's a good sign that top 25% is including new information in our model. My adjusted R squared now is 0.3258. So, looking at the multiple R squared of 0.3284, this model with all three of these variables included is explaining about 33% of the variance in graduation rates. So that's substantially better than any of the models that we have gotten previously. So this does seem to be a worthwhile addition to our model. Instead of doing an ANOVA, which of course I encourage you to do, let's take a look at the diagnostic plot for this. We've gotten much more complicated. Let's take a look at this. All right, so the first is going to be the residual plot. Even though we have a categorical explainer and a second quantitative explainer, we're going to interpret our residual plot exactly the same way. If this is a good candidate for a multiple linear regression, then we shouldn't see any particular shape here. We should just get a cloud with a horizontal-ish red line through the middle. And in fact, that's the case. So the model, would seem to be appropriate. Next is the residual plot. Again, looking pretty good. We've got a little bit of tapering down here. Nothing too radical. Next, scale location. This indicates whether or not we have homoscedasticity. In other words, uniform variances across values of our explanatory variables. This is looking good. And our outlier plot, also not looking too bad. Things do get a little spread out here, but nothing anywhere near the threshold for Cook's distance. Okay, so that's all I really wanted to do with this. Just to finish up, as I wrap up, let me just say, we've got, 3 different models here, 4 different models floating around. And so the next question I kind of have is there a more efficient way to compare these? I just sort of typed in summary for each one and looked at the multiple R squared. I would like to be able to keep track of this a little bit better, perhaps even in a tidy fashion. That'll get particularly important as I start to get more and more models. I'd like to have a solution for that. So the next vid I'm going to record is going to be on the Broom package, which is going to give us some tools for that. All right. Thanks, everybody.